Good day, everyone. I would like to briefly present this work where graph filters are designed to compute subspace projections in a decentralized fashion in an approximately minimal number of iterations. As we know, wireless sensor networks find a large number of applications across many different domains. And since sensors are typically powered by batteries, energy efficiency is extremely important to maximize the operational lifetime of the network. So these and other reasons motivate decentralized processing. And this work contributes in this direction by developing an algorithm for computing subspace projections in a decentralized fashion with a small number of interactions between neighbors. So to describe what decentralized subspace projection is, let us represent the wireless sensor network using a graph where each vertex corresponds to a sensor and there is an edge between two vertices if the corresponding sensors can communicate directly through their wireless interfaces. The Z1, Z2, and so on will denote the measurements or observations, and all of them will be collected into this vector, which is typically referred to as a graph signal to emphasize the existence of an underlying topology. Under the extensively used linear signal model, the graph signal can be decomposed as a signal term plus noise. The signal term lies in a certain signal subspace, so it can be expressed as the product of a given tall matrix U parallel and a vector alpha. So the columns of this matrix are assumed orthonormal without any loss of generality, and the number of columns, which is equal to the dimension of the signal subspace, is represented by R here. The problem is given the observations as well as this signal defining the signal subspace to find psi, the signal term. So it's like the denoising problem. And the perhaps most classical estimator to solve this problem is the least squares estimator, which projects the vector of observations onto the signal subspace. So this can be written as this product of projection matrix and Z, where the projection matrix is given by this product here due to the fact that these columns are orthonormal. So the problem of subspace projection is essentially a least squares problem, and therefore it finds a large number of applications and inference with wireless sensor networks. So the problem here is to compute these subspace projections in a decentralized fashion, so using only local interactions among sensors. Several works in the literature considered the decentralized subspace projection problem. Some of them try to maximize the convergence rate, but the convergence is only asymptotic. Others attain a convergence in a finite number of iterations, but they assume that the weights of the graph are for a graph filter are given, but this is not often the case, right? So this work tries to fill this gap by providing an algorithm that obtains the weights of the graph for convergence in a finite and approximately minimal number of iterations. The proposed approach is based on graph filters, so let us briefly review what a graph filter is. To that end, we need to review the notion of a shift matrix, which is nothing but a matrix of size a number of nodes by a number of nodes that has the same support, broadly speaking, as the adjacency matrix. So if we multiply a graph signal times a shift matrix, then what we obtain is clearly another graph signal, because this is a vector of length n, and just by the definition of matrix vector product, the nth entry of y is given by this sum here. So if we just use this property, we observe that the entry of y corresponding to the nth sensor is a linear combination of the entries of z corresponding to the neighbors of n. So this means that if each sensor stores one entry of z and computes one entry of y, then this can be implemented in just by interactions with neighbors, right, in a decentralized fashion. And this can be performed multiple times, right, just by multiple rounds of local exchanges. And if one takes a linear combination of these graph signals here, one would be computing a graph filter, essentially. So it is clear that a graph filter can be implemented in a decentralized fashion just by, in this case, L-1 local exchanges. So if this is the desired subspace projection, and this is what we can implement using a graph filter, the problem is given the subspace and the topology of the graph, we will try to find a symmetric shift matrix S, right? So we focus on symmetric shifts, as well as the coefficients of the filter, so that the output of the graph filter equals the desired subspace projection. And we want to do this in an approximately a minimal number of local exchanges. So our goal is can be phrased in this way. So let us try to characterize the family of shift matrices for which there exist coefficients C such that this equation holds. So to this end, let's start by decomposing matrix S as the sum of two matrices. The first one is such that its columns span the signal subspace, and the columns of the second one are orthogonal to the signal subspace. So this can always be done, and we can easily see that this matrix must be expressible in this way, where F is a square, is a symmetric matrix, and one can take the eigenvalue decomposition of this matrix to write it in this way, where the columns of V perpendicular are orthogonal to the columns of U parallel. And if we additionally take the eigenvalue decomposition of F, this expression can be written in matrix form in this way. Okay, so this is on the one hand. On the other hand, this product here can be clearly written in this way, because this matrix E that shows up in this eigenvalue decomposition is orthogonal. Okay, so one can just substitute this expression here and this expression here to arrive at this equality. These terms, the red matrices cancel, so that what we obtain is this system of equations. This is a van der Monde system of equations, where these coefficients are the eigenvalues of these matrices, S parallel and S perpendicular, and these are the coefficients of the filter. So to sum up, the problem is to find the minimum L for which this equation holds. So the key realization is that given a shift matrix, so given these eigenvalues, the minimum L for which this equation has a solution equals the number of different eigenvalues that are here, right? But of course, there cannot be the same eigenvalue cannot be both here and here, right? Because otherwise the system has no solution. So to minimize the number of the different eigenvalues, one can think of promoting sparsity in a vector that contains the pairwise differences between eigenvalues, both of the eigenvalues of this part and the eigenvalues of this part. We don't want to mix because otherwise we may end up having the same eigenvalue in both places, right? So this can be done as usual with an promoting sparsity can be done by an L1 norm objective, right? And if one just collects the constraints on these matrices S parallel and S perpendicular, one would arrive at this problem. However, it is easy to see that this is not a convex problem, right? Due to this the presence of these eigenvalues of these optimization variables. However, here it is interesting to see that this can be rewritten as this nuclear norm of this Kronecker difference here, and the same happens with this second term. So now what we have here is a convex problem that we can solve using standard methods such as subgradient descent or proximal or AVMM, right? So to sum up, this work develops a framework for fast subspace projection using graph filters based on the convex relaxation approach that I just explained with this this nuclear norm of a Kronecker difference. There are other things that I don't have time to explain. One of them is that the work also proposes an algorithm for obtaining graph filters capable of approximating projections that cannot be computed exactly using a certain topology or a given topology. Also, solvers for the resulting optimization problems are proposed using the alternating direction method of multipliers, and also some theoretical analysis of when it is feasible to obtain the projection exactly with a given topology. The simulations are performed using two random graph models, and the signals as well as the subspace are generated randomly. The proposed algorithms are compared with with four competing alternatives in the literature. So this figure compares the normalized mean projection error, which is defined in this way, where this is the target projection, right, and this is the graph filter, right. The averaging takes place across graph realizations and subspace realizations, right? So here we can see that the proposed method in red converges much faster than these alternatives. One may think that this convergence looks asymptotic, but this is just the effect of the Monte Carlo averaging, right? So in each realization, convergence goes, it goes to, the error goes to 0 in a finite number of local exchanges. And this is a comparison of the normalized mean square error, right, which is defined as the relative error in the projection. Okay, so here we see that the proposed method in red converges faster, or even much faster than these alternatives in the literature. So just to wrap up, we said that many inference tasks can be posed as a subspace projection problem, and this subspace projection can be obtained in a decentralized fashion using graph filters. So here we try to minimize the number of local exchanges needed to obtain those subspace projections using graph filters, both exactly and approximately. And as future research, we can extend this to tests. I mean, we should perform tests with real data, and also one can extend this framework not just to subspace projections, but to arbitrary functions. So this is all. Thank you very much for your attention.